Hey everyone, welcome to yet another episode of YinsPy. Today we're going to be talking about something very simple. We're going to be talking about gradient descent algorithm and how to implement that in Python. Here I have my Jupyter Lab open, so let's get this thing started. First of all, let me import my library. Here I have libraries. I'm going to say import numpy as np, import matplotlib.pyplot as plt, and I'm gonna do a matplotlib inline, and then we're gonna use the style that's used in RStudio, and it's called ggplot. I'm gonna do this style.use ggplot. That's my environment. Let's get that set up. Now here's the interesting thing. Before we get started, let's talk about data. Let me make a new box, turn that into the message, and then here we're gonna say create data. So we're gonna generate data by the following. We're gonna set up a theta 0, let's say that's 4, and then theta 1, let's say that's 3. And then we're gonna add noise as well as generate your x and your y. So that being said, that's how the data looks like. Let's implement that in Python. Here we have x equals 2 times np.random.ren, and let's give it 100 data points. We have y to be a linear model, right? And it's going to be 4 plus 3 times x plus your noise, which is np random rand n, and give it 100 data points 1. And notice that this y is going to be a linear model with your theta 0 and theta 1. And that's our model. So before we move on to the gradient descent implementation, let's take a look what's this data look like. So we're going to say visualization. For example, we do plot x, y as your bias, right? And then we're going to do plot x label. We're going to say x, and then we're going to do font size equals to 10. Plot y label, and that's going to be your y. Font size to be 10, and then we're going to introduce a rotation to be 0. And then we have plot axis to be 0 to 0, 15. So that's going to give you a dotted plot, which is a scatter plot. So with that in our head, that's your linear model. If you're going to analyze it, it goes something like this, right? So you have x, b, that's your bias, np.c, and then you have your np1s. Inside you give it a shape in a tuple, that's 100 by 1, and then outside of parentheses, it's going to be your x. Your theta best is going to be np linear algebra inverse x underscore b dot t dot product of x underscore b, and then you do dot x underscore b transpose dot with y, and then you print it out and you say, hey, this is theta best. You print that out, it's about 3.6 and 3.2. So as you can see, it's close to 4 and 3. It's not quite close and not as accurate as we want, but that's okay, we're going to improve it. So now let's talk about gradient descent. Before we move on to the algorithm in Python, let's talk about the structure and the math. Here I can say gradient descent. First thing we're going to do is we come up with a cost function. And then we're going to say j theta equal to half sum I equals to 1 to the superscript m, and then here we have a parenthesis, square. So as you can imagine, it looks something like mean square error. Inside this parenthesis, we have two things, okay? So we have our guess and real value. So exactly what this guess is, it's going to be a function, and let's call it h. Now this h just means it's a hypothesis. And then inside of this h, we have theta, and that's going to be your parameters. And of course, we can subscript this by the ith index. Now what's real? Real is your actual y, and you can subscript that by index I, and that gives you your cost function. After that, you can compute the gradient. So here we say compute gradient. And gradient is going to be a partial derivative, right? So we're going to say fraction partial j theta over partial theta. And then this thing is going to equal to 1 over m summation subscript I, a parenthesis, c dot, and it's going to be the chain rule, x subscript j. Exactly what's in this parenthesis is your difference between your hypothesis and your real value y. And what's in this hypothesis is going to be theta. And then afterwards, you can update. And you say, next, we update our parameters. Theta 0, theta 1, etc. So you hit enter, that's your math. So with that in our head, let's get started with the implementation in Python. So first of all, you define a function. You say cal underscore cost, that means to compute the cost function. You have a theta, which is your parameter, you have your x, and you have your y. Column, here you say length is m. Right, let's get that set up first, and then we have our predictions. That's going to be a dot product between x and theta, and then you have your cost to be, you call this equation up, this j equation up, and it's going to be a half times m times np sum, okay? And then in this np sum, you have np dot square parenthesis predictions minus y, and then you return the cost. That's your compute cost function. It's called cal cost. The next thing we're going to do is a core component of the gradient descent. So we're going to define a function called gradient descent. And we have an x covariate matrix. We have y response variable. We have theta, your parameter. We have your learning rate. Let's initialize that by 0.01. We have our iterations. Let's say this is 100. Column. And in this algorithm, first of all, we're going to set up m to be the total length of your data. And then we have a cost history, which is initialized by zeros. This might confuse you, but it's okay. Each round, we're going to update this cost. And also, we're going to update our theta. So we're going to say theta history equals to np zeros iterations by 2. And then we can update our parameters. So we're going to say this is going to be a for loop, right? So for it in range iterations column, we're going to do the following. We're going to compute the prediction first, and that's going to be the forward pass. It's going to be a dot product with x and theta, and then we can compute our theta. In this sense, we're going to do theta, and that's going to be redefined as theta minus 1 over m times learning rate times parenthesis x dot transpose dot product prediction minus y. After that, we're going to do theta. So theta history. Let's scroll down a little bit. So this line we update theta, right? So after that we want to store the theta value in our data, and in this case the data structure is going to be NP0s here. So theta history, right? I'm gonna say at this iteration IT, okay, we're gonna store this data theta t in here, and this t means transpose. We're gonna do the same with our cost. So cost history, IT column, that's gonna equal to cal cost theta x and your y. And then when all of this is done, you return theta cost history theta history, and you're done. That's your gradient descent algorithm. So now you have all the building blocks, you have all the pieces, you have all the functions. Let's train it. So here we're gonna say training in progress. We're gonna initialize this with LR, which is the learning rate, equals to 0.01. Number of iterations, we're gonna say 1,000. Theta, we're gonna initialize it with random numbers. np.random n 2 by 1, that's your size. Your bias term is going to be np.c underscore np1s, the length of x by 1. And then outside of parentheses is going to be x. And then we update, and then we define theta cost history theta history equal to gradient descent. And then inside of it we throw in xb, y, theta, your parameters, learning rate, LR, and number of iterations. Last but not least, we print the output. So we're going to say output display, and we're going to print theta 0 column. This bracket here means it's a function. I'm going to do 0.3 f comma a new line theta 1 column. I'm going to do bracket column 0.3 f, and then close that quotation mark, dot format theta 0 0 theta 1 0. Last but not least, I'm going to print out, okay, the parenthesis is fixed. Last but not least, we have final cost column curly bracket column 0.3 f, and then here we're going to say format is going to be cost history -1. Okay, so let's run this code. I have an error somewhere here. This is one dimension, so there shouldn't be this column here. Let's rerun this function. Let's rerun this. There's another typo here, format. Great, now this is done. So we have our theta 0 to be 3.5, have theta 1 to be 3.37, and as you can see, it's very much closer to this initial value that we defined. So if you want this to be a little bit more accurate, I believe we can change this to, say 2000. We run that, and the number is going to be much close. And the actual number is 4 and 3. Here we have 3.6 and 3.2. Now, if you change this to 3000, the result should be much better, 3.6 and 3.2. So let's plot it. So plot performance. Okay, so here we're going to do a fig x equal to plt dot subplots. Fig size is going to be, let's say 10 by 8. And then we're going to define our x with set y label, okay, to be j theta, and then going to be x label, so ax dot set x label iterations. Alright, so that's your x and y axis. Now we're going to do underscore equal x dot plot range as number of iterations niter comma cost history. Boom, there you go. So the x-axis is number of iterations, the y-axis is your cost, and as you can see, when you're training and when you're moving on per iteration, your cost is dropping. So there you go. I hope you liked today's episode. If you want to support the channel, give it a like and click that subscribe button, and I'll see you in the next episode.